Hey everyone, welcome back to AI Paper Podcast. Today we are going deep on a paper that really challenges assumptions about how we use these powerful vision language models, specifically CLVP. It's called Across the Gap, Exposing the Intra-modal Misalignment in CLVP via Modality Inversion. And it is packed with insights that I think any AI researcher or ML engineer working with VLMs should know about. So for our short form viewers, let me give you the TLDR right up front. This paper tackles a subtle but potentially big issue with how many people are using CLIP for tasks like image-to-image retrieval. The key takeaway is this. CLIP's training prioritizes aligning image and text representations. We call that inter-modal alignment. But it doesn't focus much on how similar images are to each other or text to each other, which is intra-modal alignment. This leads to something called intra-modal misalignment, which can hurt performance in tasks that rely on comparing images or text directly. The authors propose a clever solution using modality inversion techniques like optimization-based textual inversion, OTI, and optimization-based visual inversion, OVI, to transform these intermodal tasks into intermodal ones.
By essentially crossing the modality gap, they leverage CLIP's strength in intermodal alignment to boost performance in tasks that might seem purely visual or textual at first glance. Think of it this way. If you're building an image search engine, you might intuitively want to compare images directly. This paper suggests that with CLIP, it might be more effective to first convert your query image into a text representation and then compare it to the text representations of other images. Sounds counterintuitive, right? So we're diving deep. All right, now for everyone still with us, let's unpack this in detail. I've got our expert here to help break it all down. What really struck me about this paper is this idea of a modality gap. Can you explain what that is and why it matters in the context of CLIP?
Well, what's fascinating here is that CLIP by design learns to embed images and text into a shared latent space. The goal during training is to make sure an image and its corresponding caption have similar embeddings. However, the model isn't explicitly optimized to ensure that images cluster nicely by visual similarity or texts by semantic similarity. This creates a gap between how CLIP represents visual and textual information, the modality gap.
So it's not that CLIP is doing anything wrong, it's just that its primary focus is on this cross-modal matching, not on the finer-grained relationships within each modality.
Precisely, and the paper demonstrates how this can lead to unexpected consequences. For example, imagine looking at the embeddings for a set of dog and cat images. The distances between the dog and cat image embeddings might not accurately reflect the perceptual differences between those categories, but when you look at the text embeddings for dog and cat, the distance between those embeddings could be much larger, more representative of the semantic distinction.
So it's like CLIP has a really clear understanding of how dog and cat differ conceptually, but might struggle to organize images in a way that perfectly mirrors those distinctions.
Exactly, and that's where this concept of intra-modal misalignment comes in. CLIP's internal representations within a single modality, be it image or text, might not be as well aligned as its representations across modalities.
And the authors argue that this misalignment can actually cause problems when we use CLIP for tasks that are inherently intramodal, like searching for visually similar images or finding related text snippets.
Yes, if we rely solely on CLIP's image embeddings for image-to-image retrieval, for instance, we might miss out on capturing subtle visual similarities that are crucial for accurate retrieval. The same logic applies to text-to-text retrieval tasks.
Okay. Starting to see how this could be a significant issue.
Yeah.
So what do the authors propose? Do we need to ditch CLIP for these kinds of tasks and look for models that specifically focus on intramodal alignment?
Not necessarily. Their solution is surprisingly elegant. They propose using modality inversion techniques to essentially bridge this modality gap.
I'm intrigued. Tell me more about these modality inversion techniques.
They explore two main approaches: optimization-based textual inversion, or OTI, and optimization-based visual inversion, or OVI. Both operate on the principle of converting a task from one modality to another, leveraging CLP's intermodal alignment strength.
So instead of directly comparing images to find similar ones, we could use OTI to convert each image into a text representation and then compare those text representations.
Exactly. It sounds counterintuitive, but the results are compelling. OTI essentially finds the best text description for an image within CLIP's vocabulary.
And OVI does the opposite, right? It takes a text input and generates a kind of pseudo-image that exists within CLIP's visual feature space.
Precisely. It's like creating a visual echo of the text that CLI can then understand and compare to other visual features.
This is blowing my mind already, and we haven't even gotten to the results yet.
The results are indeed quite impressive. The authors demonstrate that using OTI for image-to-image retrieval leads to consistent performance improvements across a variety of datasets. They tested on datasets like CUD, which focuses on bird species, and RParis, a dataset of architectural landmarks. In each case, using OTI to bridge the modality gap yielded better retrieval results compared to relying solely on CLIP's image embeddings.
So instead of asking CLIP, hey, which of these images look the most alike visually, we're essentially asking it, hey, which of these images have the most similar textual descriptions? And because CLIP is so good at matching images and text, this indirect approach actually works better.
That's a great way to put it. And they see a similar pattern with text-to-text retrieval using OVI. By converting text queries into these visual echoes, they were able to improve performance on tasks involving image captions.
This is really making me rethink how we approach these seemingly simple tasks with CLIP. That's like we've been trying to speed to it in one language when it's much more fluent in another.
I like that analogy. And to really drive the point home, the authors conducted another set of experiments that I found particularly clever. They took an inherently intermodal task, zero-shot image classification, and tried to make it intramodal by applying OTI to the images or OVI to the text prompts.
Yeah, and I'm guessing that backfired spectacularly.
It did. They found that forcing this intermodal task into an intramodal framework actually hurt performance. It highlights that modality inversion itself isn't some magic bullet. It's all about aligning the task with CLIP's strengths, that powerful intermodal alignment it's been trained for.
This is already making me question some of my own assumptions about using CLIP. But before we delve further into the specifics of OTI and OVI, let's take a closer look at why modality inversion works. What's going on under the hood that leads to these performance improvements?
The authors provide some insightful analyses and visualizations to explain this. What they found is that when you use OTI to convert an image into a text representation, you're essentially repositioning those image features in a way that aligns better with CLIP's internal understanding of the relationship between visuals and language.
So it's not that OTI is adding new information to the image features. It's more about moving them to a location in the embedding space where CLIP can make more accurate comparisons.
Exactly. It's a subtle but crucial distinction. OTI isn't magically imbuing the image features with more information. It's simply aligning them with CLIP's internal representation of language, where the model is already very good at making fine-grained distinctions.
This is fascinating. It's like we're getting a glimpse into the mind of CLIP and seeing how these subtle shifts in feature representations can have a profound impact on performance.
I agree. It highlights the importance of not just using these powerful models, but also understanding how they work internally so we can apply them effectively.
Now, all of this raises a big question. If intramodal misalignment is such a significant issue, can we do anything about it at the training level? Is there a way to bake in better intramodal alignment right from the start during the pre-training phase?
That's an excellent question, and one that the authors touch on by examining a model called SLIP, unlike CLIP, which focuses solely on aligning images and their corresponding captions. SLIP incorporates an additional loss term during training to encourage better intramodal alignment.
So instead of just focusing on the cross-modal matching game, SLIP is also trying to make sure that similar things within the same modality are clustered together in the embedding space.
Exactly. SLIP borrows a trick from the self-supervised learning world, specifically SimCLR. It encourages the model to generate similar embeddings for different augmented views of the same image.
So if you take an image of a dog and rotate it, crop it slightly, or adjust the colors, SLIP wants to make sure that all those variations still end up with very similar image embeddings.
Precisely. It's essentially telling the model, hey, even though these images look slightly different on the surface, they still represent the same underlying concept, so make sure their representations reflect that similarity.
And what did they find? Does incorporating this intramodal constraint during training actually help with the misalignment issue?
Their results suggest it does. When they evaluated SLIP on image-to-image retrieval tasks, the performance using OTI inverted features was practically identical to using the raw image features.
So it's like SLIP is doing a better job of organizing the embedding space from the get-go, so we don't need to rely on OTI as much to bridge the modality gap.
That's a great way to put it. It indicates that incorporating intramodal objectives into the training process can indeed help mitigate the issue of misalignment.
This makes me wonder, could this be a direction for the future of VLM training? Could we develop new training paradigms that encourage both intermodal A and D intramodal alignment, giving us the best of both worlds?
I think that's a very promising avenue for research. Can we find the right balance in the training process to create models that excel at both matching across modalities and capturing fine-grained similarities within each modality? It's a fascinating challenge.
Now, before we move on, I want to circle back to something we mentioned earlier, this idea of a connection between the modality gap and intra-modal misalignment. The authors found that narrowing the modality gap actually seemed to reduce the performance advantage of using OTI. Can you explain what they did and why this is so interesting?
Sure. They experimented with fine-tuning CLIP using a higher temperature parameter. This is a known technique for shrinking the modality gap, essentially bringing the image and text representations closer together in the embedding space.
So it's like tightening the bond between images and text in CLIP's internal world.
Exactly. And what they observed was that in the scenario where the modality gap was smaller, OTI provided less of a performance boost for image-to-image retrieval.
It's like if images and text are already living in close proximity within the model's embedding space, there's less need to build bridges between them using techniques like OTI.
Precisely. It suggests that a narrower modality gap might lead to better intramodal alignment naturally without needing us to explicitly translate everything into the other modality.
This is really making me think about the potential trade-offs involved. On the one hand, we want to narrow the modality gap to improve performance on intramodal tasks. But on the other hand, a wider gap might actually be beneficial for certain intramodal tasks. It's a complex landscape.
It definitely is. And it highlights the need for careful consideration and experimentation when working with these models. There's no one-size-fits-all solution.
Well, before we get too carried away with the future of VLMs, I want to make sure we give our listeners a concrete understanding of how OTI and OVI actually work. Can we dive into the nuts and bolts of these techniques?
Absolutely. Let's start with optimization-based textual inversion, or OTI. Imagine you have an image, and you want to find its best representation in CLIP's text embedding space. We're essentially looking for the most accurate textual doppelganger for that image.
So if we have a picture of, say, a golden retriever puppy, we want to find the combination of words in CLIP's vocabulary that best captures the essence of that puppy.
Exactly. And OTI does this by iteratively optimizing a set of special tokens called pseudotokens. These aren't real words from CLIP's vocabulary, but they exist in the same token embedding space.
Okay, so these pseudotokens are like blank slates that OTI can mold into the perfect textual representation of the image.
Precisely. You start with these randomly initialized pseudotokens and feed them along with a simple template sentence like a photo of pseudotoken into CLIP's text encoder.
So the input to the text encoder would be something like a photo of random gibberish.
Essentially, yes. And the text encoder generates a text embedding from this input. Meanwhile, you also extract the image embedding from CLIP's image encoder for the original image.
So now we have two embeddings, one from the image itself and one from this pseudotoken concoction. And I'm guessing the goal of OTI is to bring these two embeddings as close together as possible.
You got it. OTI uses a cosine similarity loss to measure the distance between these two embeddings. And through an optimization process, typically gradient descent, it tweaks those pseudotokens until the text embedding aligns as closely as possible with the image embedding.
So it's like OTI is playing a game of hot and cold with those pseudotokens nudging them around in the embedding space until the text embedding perfectly captures the essence of the image.
That's a great way to visualize it. And the beauty of this approach is that it happens without needing any additional training data or external models. It all operates within CLIP's existing architecture.
So it's incredibly efficient and flexible. Now let's flip things over and talk about optimization-based visual inversion, or OVI. This time we're starting with text and trying to find its visual representation within CLIP, right?
Exactly. But there's a slight wrinkle here because OVI only works with VIT-based image encoders. Remember those patches that VITs use to break down images?
Yeah, those little squares of visual information.
OVI worked by optimizing a set of what we call pseudo-patches. These are like visual building blocks that exist in CLIP's patch embedding space.
Okay, so instead of pseudotokens, we have pseudopatches. And the goal is to arrange these pseudopatches in a way that creates a visual echo of the text input.
Precisely. Similar to OTI, you start with randomly initialized pseudopatches and feed them into the VIT-based image encoder.
But hold on, how do you feed pseudopatches into an image encoder that's expecting a whole image?
That's where it gets a bit tricky, because VITs have fixed positional embeddings. You need to have a specific number of patches as input. If you have fewer pseudopatches than required, you can use techniques like nearest neighbor interpolation to repeat them and fill in the gaps.
So you're essentially tiling those pseudopatches to create a kind of pseudo-image that the VIT can process.
Exactly. And once the BIT processes these pseudo-patches, it produces a visual embedding. OVI then compares this visual embedding to the text embedding of the original text prompt using that same cosine similarity loss we talked about with OTI.
So just like with OTI, the optimization process is all about minimizing the distance between those two embeddings.
Precisely, OVI tweaks those pseudo patches, those visual building blocks, until they create a visual representation that aligns as closely as possible with the meaning of the text.
Okay, I think I'm starting to get the hang of this. But both OTI and OVI rely on optimization, right? Can you give us a more concrete sense of what that actually means in practice? What's happening under the hood?
Sure. Both techniques utilize gradient descent, a common optimization algorithm in machine learning. They calculate how much the loss changes with respect to each pseudo token or pseudo patch, and then update those values in a direction that reduces the loss.
So it's like finding the downhill slope on a lost landscape and gradually making your way down to the lowest point, which represents the best alignment between the two modalities.
Yes. That's a great analogy. The optimization process iteratively refines the pseudo-tokens or pseudo-patches, bringing the text and image representations closer together step by step.
This is a really elegant approach. You're not changing CLIP's weights or adding new data. You're just using optimization to leverage its existing knowledge to perform these modality inversions.
Exactly. And because OTI and OVI operate at this single feature level, they're remarkably flexible. You can apply them to individual images or text prompts without needing to train separate models or rely on large external datasets.
That makes a lot of sense. Now, before we move on to the next section, I'd love to hear your thoughts on the computational cost of these techniques. These are optimization-based, so they involve multiple iterations. Does that mean they're really computationally expensive?
That's a valid question. The paper does acknowledge that techniques like OTI and OVI require some computational overhead. They're not as simple as a single forward pass through CLIP.
So it's not exactly a free lunch. There's a cost associated with this performance boost.
Right. However, it's important to remember that OTI and OVI operate at a single feature level. You're only optimizing a small set of pseudo tokens or pseudo patches for each image or text input. It's not like you're training a whole new model from scratch.
So while there's a computational cost, it's not prohibitively expensive, especially when you consider the performance gains you can achieve.
That's a fair assessment. And it's worth noting that ongoing research is exploring ways to make these techniques even more efficient.
Okay, great. Now, one last question before we move on.
Yeah.
How do we know that the performance improvement we see with OTI and OVI is actually due to bridging the modality gap and not some other artifact of the inversion process itself?
That's an excellent question. The authors address this by analyzing how the performance of OTI changes as you increase the number of optimization steps.
And what did they find? Does the performance just keep getting better the longer you optimize?
Interestingly, no. They observed that the best performance is actually achieved after a relatively small number of optimization steps. If you keep optimizing, the performance eventually starts to decline.
That's fascinating. Why would that happen?
They argue that this decline occurs because as you optimize for a very long time, those OTI inverted features start to drift away from the text manifold and back towards the image manifold.
So it's like they become too similar to the original image features and lose that special something that made them so effective at bridging the modality gap.
Exactly. To further support this, they've visualized the distribution of cosine similarities between image-image, text-image, and OTI-image feature pairs at different points in the optimization process. And what they found was that at the point of peak performance, the OTI image similarities closely resembled the text-image similarities. But as optimization continued, they started to look more like the image-image similarities.
That's a really elegant way to demonstrate that the effectiveness of OTI stems from aligning those image features with the text manifold, not just from the optimization process itself.
It is, and it speaks to the importance of understanding these subtle dynamics when working with these powerful models.
Now, it's clear that modality inversion techniques like OTI and OVI can be valuable tools when working with VLMs like CLIP. But as we've seen, there's also a lot of nuance to their application. What other exciting avenues for future research do you think this paper opens up?
It seems like this paper is really just the tip of the iceberg when it comes to understanding and addressing intra-modal misalignment in VLMs. I think there's so much more we can explore.
Yeah, totally. It feels like there's a ton of different directions we could go from here. What are some of the most exciting avenues for future research that you think this paper opens up?
One that immediately comes to mind is exploring alternative training objectives that could explicitly encourage both inter and intramodal alignment. We saw how SLA incorporates a self-supervised loss to promote that intramodal alignment, but I think there's a vast space of possibilities there to explore.
So we could maybe devise some new loss functions that can strike a more delicate balance between those two types of alignment, or even maybe dynamically adjust the emphasis during training.
Yeah, exactly. We could maybe have like a curriculum-based approach where the model first focuses heavily on intermodal alignment and then maybe gradually introduces more of those intramodal constraints as training progresses.
That's interesting. So it's almost like teaching a child to first understand the relationship between words and objects, and then later you kind of refine their ability to categorize and differentiate within those categories.
Yeah, that's a great analogy. I think it also highlights the potential for drawing inspiration from developmental psychology and cognitive science when we're trying to think about new training paradigms for these VLMs.
For sure. And beyond even just like the loss function itself, I think another area that I find really intriguing is the potential for architectural innovations. Like, could we design new VLM architectures that are just inherently better at capturing both of those inter and intramodal relationships?
Yeah, I think that's super promising. Maybe we can explore architectures that have some dedicated pathways for processing intramodal information, so that way the model can develop more specialized representations for, doing within modality comparisons.
Mm-hmm. Yeah, and or maybe even some mechanism that can allow the model to dynamically adjust the weighting of different pathways depending on the task at hand.
Totally. That's a really cool idea. So it can kind of seamlessly switch between prioritizing intermodal and intramodal alignment based on, what it needs to do.
This whole paper has really opened my eyes to the interplay between these two types of alignment in VLMs. It's not just about bridging the gap between these modalities, but also making sure that the representations within each modality are well structured and meaningful.
100%. It's a good reminder that we're still early on in this, figuring out how to train and use these powerful models really effectively. There's just so much more room for us to keep innovating and keep discovering.
Yeah, well, on that note of excitement and anticipation for the future of VLMs, we'll wrap up this episode of AI Paper Podcasts. Thanks so much for joining us on this deep dive into the fascinating world of intra-modal misalignment and CLIP. I hope this episode has given you a new perspective on how these powerful models work and maybe even spark some ideas for your own research.
It's been a pleasure discussing this paper with you.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with AI.